do a little review for the exam on Tuesday, take questions. Tuesday, chapter 5 and 6 material. The homeworks since the last exam. So homeworks 5, 6, 7, 8, and 9. In there, there's a sheet of paper. Write on both sides. So you write formulas for probability densities, equations, different numerical examples, and things like that to cover the material that you want to do. That's Tuesday. That's the 9th. On the syllabus, you will notice that for 11/19, next Thursday, I won't be here. There's not going to be a class that day. Something was planned for a long time ahead. Last class, we handed out the projects. And we'll be going into chapter 7 when we come back after that. So you can use that day to think about projects. One of the options for projects was to do some other problems that weren't done, or a section or a part of a book that we haven't covered, or done something with. So it would be an opportunity to spend time doing that, giving an idea about what you want to do. One option was to look at some videos online and review those, review some other teaching material online, and so you could spend an hour doing that and get a broad idea of what you'd like to do with the project. The semester goes pretty fast toward the end because there's even though it doesn't affect our Tuesday, Thursday classes, there will be breaks around Easter. There's a short week, the last week of classes, so spending some time getting some idea what you want to do for the project, or you have something that you're pretty sure you want to do, making some steps to get a little deeper into it will really benefit you. And if you look ahead to the material on chapter 7 on transformations, then you'll just be ready when we discuss that to be doing it. So the class won't meet on this Thursday, but we have the exam on Tuesday. So any questions about that? So for review, I have a particular a problem to look at that's kind of like material on this last homework. So I thought we'll do that problem and then kind of open it up for questions, whatever you want to talk about. Right? And so let's say that y is a variable, and given some parameter lambda, it's Poisson. That means that the probability that y equals the value given lambda, keep the lambda in the picture there, which, although it's a discrete probability, just to have a consistent notation, we'll write it as a little f of y. And so the Poisson at lambda to the y, e to the negative lambda, over y factorial. Now this discrete distributions were really on the last exam. They feature to some degree in this one, particularly these hierarchical or two-stage models. So if there's a discrete distribution that you need to know, I'll give you a few facts about it on the page. So you don't need to write down everything about the discrete distributions. You can write whatever you want you think would be useful, but I'll try to give you more, give you a couple lines on the exam paper that describe that, what I think you need to know. Okay? But you're welcome to make short notes of anything if you think that would be useful, but you'll get that information, right? And so the values that y takes on are these integers. And under this model, the expectation of y given lambda is just lambda. Turns out the variance is also lambda. So really these are, if we think of lambda as something that's unknown, maybe we're going to give a distribution to it, those are really conditional means of variances. Right? Now, if lambda is unknown in a Bayesian context, people put a distribution on it. So we're going to say, what if lambda has a distribution that's exponential with a parameter theta? Right? The exponential has this, is 1 over, not of y, but the density of lambda now. So, lambda looks like a parameter or a Greek letter, but if it's uncertain, we can put a probability distribution on it, and e to the negative lambda over theta, for lambda greater than 0. Theta is also greater than 0. The parameter lambda up here is also greater than 0. So we can start out with those couple of things. The expectation of lambda is then theta, and the variance of lambda from this exponential distribution is theta squared. So y is going to be the thing that we're going to measure. So what's the average value and what's the variance of y, our observations, realizing that lambda has this randomness, this uncertainty with it. Right? So what's just the marginal expectation of y? Well, that's our expectation of y, and it's the expectation, the initial expectation. And so this formula would be a good one to have on there, surely. So given lambda, that's its expectation, but under this randomness here, that's just the prior mean theta. The variance of y then is this expectation of the conditional variance plus the variance of the conditional expectation. If you plug those things in from the distribution, expectations, the variance of y given lambda under Poisson is just lambda again, and then this one is lambda as expectation. So it's the expectation of the lambdas plus the variance of the lambda from that exponential model. So it's theta plus theta squared. When y was given lambda was Poisson, the mean and variance were the same. But marginally, the variance here is more than the mean. There's more variability because there's this randomness in the lambdas. Yeah.
So on a problem that's like similar to one like this, I think there was one on the homework where it involved a binomial, and so you ended up with like the variance of NP, and you pulled out either N or P, and when you pulled it out, you had to square it, but I didn't understand why you had to square it. I just saw that in the book.
Yeah. So in that, so if you had so if y given, lambda is Poisson, and that's the number of cases, and your variable is going to be 10 times y, $10 per item, right, per occurrence or something like that, right? Then the expectation of x was the sum of the x's over the probability that x equals one of its values by definition, and that is each value of x is 10 times y, and each x value corresponds to one and only, one y value. And so there's a correspondence here. And so the 10 pulls out, and what's left is this expectation of y. So it's through these equations, like the expectation of x is 10 times the expectation of y. This multiplier gets put there. Right? the variance of x has a similar type of thing. Right? So it's x minus the mean of x squared times the probability that x is there. But x is 10 times y. The mean of x is 10 times the mean of y. That's this part, mean of x. And this one is the mean of y. Right, 10 times what that refers to, right? So this thing, you have 10 times y minus 10 times the mean of y. That's squared. And there's this one-to-one correspondence between the probability of certain x's and certain y's. So if you pull the 10 out of that one, then it's squared. And you're going to get a 10 squared out here. Y minus the mean of y squared is the probability of this. And so that is then where the squaring comes in because of the variance. So we're going to get 100 times the variance of y in there. And in that homework problem, we're just taking in the number of trials is fixed. Right, for a given number of trials, it's a constant number, so in equations like this, it just pulls through the expectation or it pulls through the square and the variance. Right, so we can find the mean and variance, but what is the distribution of y? Right. What is y? Exactly. So the joint density of y and lambda. Y is our observed count, and lambda is this parameter that has a distribution. Right? The joint can be written as the distribution of lambda times the distribution of y given lambda. So it's one of them times the conditional distribution of the other given the first. So you can do it either way. Yeah.
And that's because the distribution of y depends on the value of lambda, right?
Yeah, so I'm writing it like this because that's how things were stated up front. The distribution of y given lambda and the distribution. This is equivalent, you can write it as the marginal distribution of y. I'll start putting a few subscripts on here. And then the conditional distribution given the other way. The relation between a joint distribution and a marginal conditional, you can do it either way, right, conditioning. This one's convenient because that's how the distributions are portrayed. But if you had the other two things, Bayes' theorem really makes a use of this relationship too. Eventually we're going to want this thing. So we're going to take these two divided by that f of y. So Bayes' theorem makes use of that. So what would it be in this case, right? So it's Poisson, right? So there's a lambda to the y, e to the negative lambda over y factorial. And this one was, that's this one. I've written them in different reversed orders. And then lambda is this e to the negative lambda over theta. Right, and so that's defined for all these values of y and lambda. Yeah. Okay. So that's just the joint density. Just multiply those two things together. At every continuous value of lambda and every integer value 0, 1, 2, and so on of y. That's the joint. To find the marginal of y by itself, we have to integrate out lambda out of this thing. I'll put a couple things up front. They don't involve lambda. And then there's a lambda to the y, e to the negative lambda. And then we'll write this as 1 over theta, I guess plus 1, right? So that's just writing it as an integral, right, and then grouping some terms together. Right, and so these type of things, right, this looks like a gamma, random variable. Lambda is continuous, 0 to infinity, just like a gamma. Lambda to a power, e to the negative lambda times something. It's kind of the form of a gamma distribution. So we'll take a little side here. Put a gamma here, right? So what does the gamma distribution look like? If lambda has a generic gamma distribution, then the density for lambda, there was 1 over gamma alpha beta to the alpha out there. And then there's a lambda to the alpha minus 1. And then the negative lambda over beta. And this thing, right, this density, right, integrates to 1. So we have something that kind of looks like this, right? Because we have lambda to a power and e to the negative lambda over, times something, which could be made into over something. And so if we had the right things out here, it would integrate to 1. So in this case, so let's pull the y factorial and 1 over theta on here. And write this as lambda y plus 1, right, minus 1, right? Because we need a minus 1 there. And then we'll write an e to the negative lambda over something. Right, so that 1 over theta plus 1 is 1 plus theta over theta. If we want it all in the denominator, then theta over 1 plus theta. So we can do a theta over 1 plus theta. So if we put the right things in there, that thing would integrate to 1. This is 1, let me make this a little bigger. Theta, 1 plus theta. This is not dissimilar to what we did to find the means of a beta or means of a gamma. Right? That there was, put an x in there, and then there was, you would kind of group powers together, and it would work out. Right, so we're going to call, in the next page, alpha is y plus 1, and our beta, 1 over beta, is going to be theta over 1 plus theta. So if we had the right normalizers, it would work out. Right, so if alpha is y plus 1, and this beta is theta over 1 plus theta, then the marginal distribution of y, we had before we had a 1 over y factorial and a, what was it? And just 1 over theta there. And now, instead of having a gamma alpha over here, we haven't included it, so it's going to end up here. Gamma y plus 1 function there. And instead of having beta to the alpha down here, you'll have beta to the alpha in the numerator, and the alpha is y plus 1. So this thing ends up being the density just for y. Y equals 0, 1, 2, etc. Like a Poisson. But this thing simplifies just a little bit, right? The gamma y plus 1 is y factorial. Because y is an integer, so it steps back 1. Right, so the y factorials cancel with that thing. So we have a 1 over theta, and a theta over 1 plus theta to the y plus 1. But if you cancel one of those, right, you get 1 over 1 plus theta. Well, let's see, you take y of them, right, and then there's a 1 over 1 plus theta, like that, right? Because there's y plus 1 things in the denominator, take y of those plus 1 more, and then you cancel one of those, it's just empty line. What does this, now, I don't know if this looks like anything. But it turns out that y is geometric. The probability of 1 over 1 plus theta of being a success. This is like p to the y times, or p, 1 minus p, p. So kind of, it just happens to be that way, right? That the count is going to be Poisson, but the rate is random number. And so if you integrate over the randomness of that, it's like having a certain geometric. Right? So if the theta is small, then you have a small expected rate. So you have small numbers, and the probability that small is pretty large, so you have a success pretty quickly. So anyway, that's how it works out. So what's the process that's important to look at? We're given that was the expectation, all the way back here, right? Given a Poisson and another one. We can use this expectation variance formulas to get mean and variance. Right? But if I ask you what's the joint density, you can multiply them together. If I ask you to get a marginal, right, you would integrate out that parameter. Right, for that. I could do this with some of these distributions. If I do it with just x and y's, x squared y or something like that, some of those end up being a little bit easier to deal with. I mean, these you kind of have to remember the relationships among some distributions and things to get it work out. So if it's going to go like that, then you need to do that to show a mean for a continuous distribution or something like that. I'd give you the densities there, so you can do the comparison to figure it out like we've done on there. It would be the same style of thing like on the homework. So, yeah.
Could you just go ahead to the next slide?
Yeah, so we get this marginal one, right? And right. We recognize that this is going to be a gamma, simplified a little bit, writing it like a gamma form. And so we should have some terms here, so we multiply with what we need down here to make it integrate to 1. Right. Then the compensation would be up here. Or another way of saying it, this integral equals what the thing that was down there that normalized it to make it to 1. So if we put that in there, that's the general form of the gamma. So we have these two parts from the densities. This is the part to equate it. And we simplify it a little bit and realize, hey, that's if y goes 0 to 1, that's the probability of the number of failures, 0, 1, 2, 3, and then a success. If theta is positive, right, 1 over 1 plus theta is between 0 and 1. If theta is 0, this would be 1. As theta gets bigger, that probability goes down. So it turns out to be geometric. So that would be a marginal thing. What is Bayes? What's the Bayesian inference? And the Bayesian inference, we would want lambda given y. So the joint distribution, right away, of both of these over y. The thing that's over here always goes in that you're conditioning on, given something, given your data, goes in the denominator. And so this is a marginal for lambda times the conditional over this marginal that we found down here. And same process. There's a, I almost remember, there's a y factorial theta there. And then there's a lambda to the y from the Poisson, and there's a negative lambda, and we could write it as that over theta plus 1 plus theta. That's how it worked out once we did that, those two pieces together. And the denominator is this integral that we just did of the stuff up top. So there's a couple ways to approach these base problems. So 1 over y factorial and the theta, right? These two things up here, they're also down here. And they're not lambdas. So those things cancel. And so what we actually are just left with is lambda to the y e to the negative lambda over theta plus 1 plus theta. And it's written like that over the integral of that numerator times d lambda. And, you know, it just looks like that gamma distribution. You know, lambda to a power, e to the negative lambda times something. Lambda is greater than 0, positive continuous value. And it turns out that, you know, lambda given y is a gamma distribution. Ted, do you have a...
Yeah, if we've already solved the integral, couldn't we just plug in?
You could just plug in what was here.
Yeah.
Yep. And then what would be, right, so right, you could just, that's the marginal.
So couldn't we just plug in that like punchline at the end, the theta over 1 plus theta to the y, 1 over 1 plus theta?
Yeah, what happens if we do that? That must be what we actually need to make this thing work out. Yeah, so if you, right, you don't go through that, right? You can plug in what we had, and there's this thing. I'll write it as +1, you know, -1. I know it's going to be like a gamma. And then this thing, theta, theta. And the thing at the bottom we figured out was theta over 1 plus theta to the y, and then there's a 1 over 1 plus theta. So the y factorial is gamma y plus 1. And it's down here. And look at this. We have theta over 1 plus theta to the y. And if this theta here goes down in the denominator, we get another copy. So this theta here kind of makes this one whole. So there's theta over 1 plus theta to the y. And then we're just left with the lambda pieces. E to the negative y over theta 1 plus theta in there. And that is the gamma density.
So wait, you're saying that 1 over 1 plus theta times 1 over theta is 1?
So 1 over theta. So if you have 1 over theta over 1 over 1 plus theta, well, that can be written as 1 over theta plus 1 plus theta. Right? So this whole thing's in the, in the denominator. So the 1 over theta, that theta is in the denominator here, but so you multiply the two things in the denominator. So it ends up being like that. So before we had y of them, if combine those two terms. You get another one, y plus 1. It should be y plus 1. I shouldn't cancel it. Yeah, that's for sure.
So,
Yep.
this seems like a rather long problem to end up on an exam. Like, I understand the concepts would probably show up, but like maybe not this kind of a distribution.
Yeah, so think about it in pieces, right? I give you these two things with a little bit of supporting information. Say, what's the expectation of y? What's the variance? So that could be parts A and B, right? But yeah, no, not to be. And then maybe it wouldn't be exactly this, so another problem, or what's the joint density, or find the marginal of something from a joint. Some of it, sometimes the integration is done with this by recognizing distributions. And the other way that type of thing gets done, if I just would give you half of x and y density. So, here's one example, kind of like that. Right? So you could have something. So here's a constant c. I don't know what it is yet. Times x times 1 minus y. And 0 is less than x, is less than 1, and 0 is less than y. If I give you this, are x and y independent? Yeah, by the factorization, they're independent. What's the marginal distribution of x? Then it's just integrating out y. C times x times minus y, just integrate out y. So there's c times, multiply that out, so it's x, so there's an x times y, and then minus xy, this gets y squared over 2. I think it's a little bit easier for me just to do that by multiplying that out, and we're integrating out y, so that goes from 0 to 1. So this is some constant, and y is 1, this is x minus x over 2, so it's c times x over 2 is the marginal density. That thing has to integrate to be 1, right? So the integral over f of x dx is supposed to be 1. So if you do that, there's an x squared over 4 going from 0 to 1. So that's c times 1/4. If that's supposed to be 1, then that c must be 4. I've done it correctly. So the marginal density of x overall is 4 times x over 2, so it's just 2x. Ends up being the marginal density for x, where x goes from 0 to 1. So another way of getting a marginal just would be integrating out 1. And if it's an explicit polynomial type structure,
Why
then
did it turn into cx over 2? Like, why did the x go away?
x minus x over 2. So just combining these two.
Oh.
So 1x and then 1/2 x.
Oh.
The y's went away because when I plugged in 1
Yeah.
or 0. So that's a little bit more maybe straightforward way to do that. But when it's a distribution, you kind of recognize that it matches up. Yeah.
Do you always have to find a constancy?
Now, sometimes I'll just give you that.
Okay.
You want it to integrate to 1, so the book style problem, some of them just give a constant there and they say what that value sees, so you got to integrate both. If I just give you the number, then you won't have to. It's just reinforcing this idea that the densities have to integrate to 1. So anyway, this particular one, right, this lambda given y ends up being a gamma distribution. And the parameters are y plus 1, that's playing the role of alpha here. And theta over 1 plus theta is playing the role of beta in that distribution. So yeah, I wouldn't I probably ask things in different pieces, right, with some guidance, right, so that it wouldn't be, there's one enormous problem, this would be, probably take, this type of, here would at least take up a couple problems, and maybe not all pieces of it, so. This little thing, this is actually one of our distributions. This one has a certain, it's a particular one. Right? If x goes from 0 to 1, right, the candidate that's most likely is this beta distribution. Right? So it could be beta, the range is right. That, let's switch to bigger again. Right? So the density, if x is a beta random variable, with 2 values, then the density of x at gamma alpha plus beta, gamma of alpha, gamma of beta, and there's an x to the alpha minus 1, and a 1 minus x to the beta minus 1. This has x in it, it doesn't have 1 minus x, but if beta is 1, then that goes away. So which one is it? X is a beta, actually. We need 1x, so alpha has to be 2, and 1 minus x is 1. So it turns out to be this particular beta density. You have a guess as to what y is? It's just 1 minus y up here. There's going to be some normalizing constant in it. So there's going to be some constant times 1 minus y. If you go through some of this, y is going to end up being beta 1, 2. Because when it's alpha is 1, the x goes away, and when beta is 2, you get 1 minus x between 0 and 1. So it ends up being that density. And they're independent because they multiply. If you take the marginal density of x times the marginal density of y, you get that thing up there with an appropriate z-score. Each density contributes a 2, multiplying it. So 2 times x, or 2 times 1 minus y, you multiply them together and you get that, the density that would be up there. So that's kind of an example, right? Expectation, conditional expectation, dealing with the joint densities, integrating one out. Are there other questions you want to ask about for the exam? Last time we did a little bit of a review of material that was on there. I could repeat a little bit of that, and just so in chapter 5, we had a marginal density that was continuous. We calculated probabilities between some ranges. We calculated a cumulative distribution function, so it's an integral up to x of that density. So sometimes we have to get the density of the cumulative. If we took the derivative of this one, it's the density. So you have the cumulative, you can differentiate it and go back that way. So, f of x is that particular density for x less than 1. The cumulative distribution, right, is just the integral from 0 up to some value of x of 2x alpha 2t, right, dt. So t squared over 2, so that goes away. So it's just x squared. The next between 0 and 1. The cumulative, technically, right, it's going up, and then once it hits 1, it's at 1, and it just goes on to 1 forever. And then 0 below that. So we get the cumulative. So a problem like, what's the chance that something like this is greater than 1/2? this is an example from the book, right? 5.11 actually happens to use this. We know that they just chosen a certain beta distribution, right? A certain beta. And they've said that this x is supposed to represent the proportion of time in a 40-hour week that an industrial robot is in operation. So maybe that describes that. What's the chance the robot's in operation more than half the time if it's in operation more than a quarter of the time? So this is both things, right, over the probability of the one we're conditioning on. This f of x, right, is really the probability that x is greater than or is less than or equal to some value, right? So the probability that x is greater than some value is 1 minus that. If x is greater than 1/2, it's certainly greater than 1/4. In that type of question, there's a little redundancy. Right? This is equivalent to the probability that x is greater than 1/2 over the probability that x is bigger than 1/4. Right, so it's 1 minus 1/2 squared over 1 minus 1/4 squared. And that simplifies to 4/5. So given that the robot is going more than a quarter of the time, so 2 hours out of every 8-hour day, kind of on average, right? The chance that it's going more than half the time, then it's about 80%. So if you have a whole big factory with many, many different robots, and you're looking at the wear and tear and their efficiency and their usefulness of things, you might be keeping track of data on how are they being used. Is the production process actually at a stage that they can make use of this expensive technology, and things like that. What else might we want to know? Expectation. On average, what's the average proportion of time that the robot is being worked? Right, expectation of x, it's going to be integral from 0 to 1 of this times f of x. So 0 to 1 x, and this thing was just 2x, right? 0 to 2, and that's x squared, so it becomes x cubed over 3. So 2/3. On average, the robot is working 2/3 of the time. If you do a similar thing, the expectation of x squared turns out to be 1/2, so the variance of x is the 1/2 minus the 2/3 squared, which ends up being 1 out of 18. Right? The standard deviation of x is the square root of that, which is about 0.24. This is about a quarter. It's not exactly a quarter, but it's pretty close to that. What if you want to convert this to hours or minutes? I switched to x here. I think was this x? Okay, those are x. Couldn't remember if I used x before. So, say you want to do hours in a 40-hour week. Well, we call it random variable h is this 40 times x, or if you want to do minutes, 40-hour week. Right? So 2,400 minutes, 60 minutes times 40 hours times X. Maybe hours or minutes are important for electricity bills and usage. Right? So I could ask you about expectation of X, then it's just H, then it's just 40 times expectation of X, and X was 2/3. So on average, so 40 times 2/3, 80/3. Expectation over here in minutes, well, that for minutes, 2,400. Expectation of X is 2/3. That one works out nicely. 800, 1,500 minutes on average. Standard deviation, you just multiply by the number again. Variance has the square of that. But what else is in it? Much else in 5. 5 looked at there were some specific examples of continuous distributions in there. In chapter 5, there was uniform between some points. You wanted to make a chart for yourself, density, expectation, and variance. Sometimes you can do the CDF, the capital F of X function, the density of the little f of X function. For some of these, you can write that down. That is useful. Exponential, gamma. There wasn't necessarily a specific CDF that's useful to work with for gamma. That's an integral that's approximated numerically. Normal with mean, and if I write standard deviation here, the variance is sigma squared, if that's the standard deviation. Beta, random variables. And there's a few where we had the moment generating functions as well. They exist for these other things, but they're not necessarily the most convenient form to use. For exponential, it was 1 minus theta t negative 1. For gamma, it was 1 minus theta t negative alpha. And for normal, it was e to the d sub t plus t squared theta squared over 2. Those were useful for some things where you could differentiate those, find the means, differentiate twice, find the second moment. We did some work, kind of in the exponential case, of showing that it's that was an integral. So and also in the problems, you'll get partial credit for writing down formulas that show progression along the way. So if it asked for the moment generating function of one of these things, well, it's e to the tx expectation. So it's an integral of e tx times the probability density of x dx. And then figuring out how it goes from there is, doing the calculus, figuring out some of the things that we did. But if you can write down, steps along the way, you'll get some points for doing that. So those are the main distributions. For normal, right, I'll give you a copy of page 448, table, the normal curve. Right, so there's a normal curve that's listed in there. Our normal curve, right? That normal curve for us gives an area between 0 and some value. So it gives this area under the normal curve. So if you wanted for a normal, what's the probability that A is less than a normal less than B? And let's say, here's our picture we're doing. So here is 0, we have some A over here, we have some B over here. Well, we would look up the probability. What numbers would we look up? We can look up B, and it will give us this area under the curve. And then if we look up negative A, this is a negative number, flip it over here, this area is the same as that area. And add those two things together, and you get the probability under the curve. But any questions about? We've talked about some examples related to 6. Right, so in chapter 6, we have 2 variables at a time. If these are both discrete, then this is a kind of a table of counts. That's up there. In yesterday, I gave them in my other classes. The 220 class has done a little bit related to that. They don't do nearly as much details about conditional expectations and some other things. And they do more on inference. It's kind of in between the two. But the exam that they got yesterday, well, that's what's on their exam, not their exam. One of the problems on there is kind of a two-way table. Oh well. Those will eventually come around, I guess. Right. But in this example, it talked about you have cars, and X is the number of full-size tires on the car, and I said 4 or 5 or 6 full-size tires on the car. I guess I could have included. Right? So 4 would be possible. I'm thinking about the 4 that are driving on the road, right? And then some cars have another full-size tire on the back. Well, a few people that go way out in the back and go off-road have an extra tire. That they might have 6, would be rare, right? And then there's the small spare tires that come with many. Some don't have small spares, and some have 1. You could have 2. I mean, you could put 3 in here because if somebody had a flat tire and put that in the shop and they're driving on their little spare, they might only have 3 regular size tires. Right? But so if you had probabilities in each of these places, this is about 90, 80. This is about 80% of the people have 5, and 15% have 4, and there's a few people who have more. You could have the marginal of this one, if that's why. How many spares do they have? Well, if they only have 4, these have to add up to that. So you might have about 13% of those. Maybe they have a lot of people have that, and very few people have an extra one. Okay. I don't know if you've noticed the network's kind of flickering on and off. That's part of that is. And a few people would have 4 regular tires but no spare at all. Right? And so if you fill that in, you'd get the marginal distribution, I mean the joint distribution of all these things. That would be the probability. And you could say, what's the marginal distribution of X, the number of full-size tires? Probably using 4 times this plus 5 times that, 6 times that. You could look at the conditional distributions of things. What's that conditional the probability of Y given that X equals 4? And so on, and calculate the probabilities, out of the 15% that's in here, 2% are here, 12 and 1. So if Y equals 0, 1, or 2, there's 2 out of 15, and 12 out of 15, and 1 out of 15. That would be 0, 1, or 2, given that they have in that category before. The idea of this problem, and I'll post that just so you can see the full question that was there in this example. So 6 had some of these discrete tables. It also had f of x, y for continuous ones. There's a second type of problem there. Are they independent, giving expectations, getting variances, getting conditional expectations, that type of stuff that we did. Are there any particular questions you want to talk about? Any types of problems, anything from the homework that you want to go over? All right, well then I'm going to subject you to just a little bit more. So we're just going to elaborate that Poisson problem just a bit. Say you had I equal, so when we just had 1, when y given lambda was Poisson, lambda, and lambda was exponential, we determined that y given this was gamma, and the parameters were y plus 1 and theta over 1 plus theta. So what's the expectation of lambda given 1? What do we think lambda is? Right? You get data, calculate the posterior distribution, that gives probabilities for lambda. What's the average? Well, it's y plus 1 times theta over 1 plus theta. That being the average. Now we're just going to leave that there. So, theta, well, we're just going to leave it like that. Right? Sure. Just leave it like that. We're now going to imagine a situation where we have a number of areas. Not just one observation, we're going to have a bunch of different areas. These could be counties. We could be counting something like cases of measles out of those. And in area I, in sub I, people are exposed. Potentially they could be exposed to catch the disease, be afflicted with something. Right? And lambda is going to be the rate per so many people, per 1,000 people, something like that. Things that are more common, like births or marriages or something, it might be a rate per 1,000 people. For rare diseases, it might be rates per 100,000 people, something like that. Right? And so y sub I is going to be the number observed, right, in area I. So, kind of the elaboration of this model would be, say, what's the distribution of lambda I, or y sub I given lambda? Well, if it's Poisson distribution has this nice clumping property that as you put together bigger and bigger pieces that are all the same Poisson, it's still Poisson. So the rate becomes the number of people are exposed times the rate per so many people. The count you would see could have that distribution. The density for the probability for one person, or one area, sorry, is Poisson. The Poisson, you get the rate here raised to the yi. You get e to the rate, or the number, the expected value, over yi factorial. So that's the probability. So each yi could be 0 people, 1 person, 2 person, etc. What's the joint density, or joint probability of all the y's given lambda? What's the joint density of y1, y2, yn given lambda? Now, we haven't done too much with this, but it's a pretty direct extension of what we would do if we just had the joint distribution of two variables. If I didn't write lambda here, we would just look at the distribution of n things. If they're independent areas, which is, like a little questionable if it's infectious disease and people crossing boundaries, but if it's independent, we generally talk, so if x and y are independent, we multiply the two densities together and got the joint if they're independent. Same thing works here. y1 given lambda times y2 given lambda, y sub n given lambda. It works when we're conditioning on something all the way across, and it works on more than just two variables. So you multiply all those things together. That's called the joint density of all those observations together. And so if each one of these has this, we can write this as a product. I going from 1 to n. This is kind of the corresponding thing to the summation over many. Summation over I going from 1 to n. This is the product. Multiply them all together. And so each one is ni lambda to the yi e to the negative ni lambda over yi factorial. We can group a few things together to make this a little neater. One thing you can't really group together, right, is the ni to the yi over yi factorial. That's one piece of it. And then there's these lambdas to the yi's. If you use lambda to the y1, lambda to the y2, etc. You could put all those together as lambda to the y1 plus y2 plus y dot 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 plus the yn. If the lambda is the same, they all have lambda to a power, and you can add all those together. There's e to the negative ni lambda. Right? You could put all those exponents together and factor out the lambda. So you get e to the negative, I'll write this n lambda, where that n is n1 plus n2 plus n, I guess I said there's n areas, whatever. So all these big areas together through this model, what's it look like? Lambda to a power and e to the negative lambda times something. Right? It's going to kind of look like a gamma, right? Or it could be, right, if lambda. We're going to have the same prior distribution, right? What is lambda? Well, that exponential distribution is pretty small, kind of sloping down. It might be larger. And this gives some idea of kind of where it might be. If you didn't have any data, you'd have had to do something, right? So we had the yi given lambda were Poisson in ni lambda, possibly different sizes, independent of one another. And then lambda being exponential theta. Well, we do things kind of like we did before and figured out the distribution, y1, y2, the posterior distribution. It turns out to be a gamma like we had before. But instead of just taking y plus 1, we have all these y added together. So it's the sum of the yi's plus 1. Before we had y plus 1, now we have all those y's added together. And yeah, this other part, before we had just negative lambda, and now we have n times lambda, and then from the prior distribution we're going to get some things, but it ends up being, so instead of just being theta over 1 plus theta, like it was before, it's theta over 1 plus n theta. We get that extra n because instead of just having negative lambda for 1 Poisson, we have n Poissons. So we have n lambda. So that's where that shows up if you work through that. Right? So that's the posterior distribution for lambda, given all of our data. And a Bayesian would use that for inference. What is lambda? I'm going to summarize that distribution to tell you what I think lambda is. One summary, what's the expectation of lambda given all our data? Well, in the general case, it's the first parameter times the second parameter. So the sum of yi plus 1 times theta plus n theta. That's what it is. Let's divide first by n in both the numerator and denominator. If we divide by n in both the numerator and denominator, right, this is y bar, and then plus 1 over n. Divide that first term by n. Divide the denominator by n, we get 1 over n plus theta. And now let's divide both the numerator and denominator by theta. So if we do that, we get y bar plus 1 over n divided by 1 over n theta plus 1. It's a different, just a re-expression of that posterior mean, the mean of this conditional posterior distribution. What happens as n gets big? Or we can ask the more extreme question, what happens as n goes to infinity? What happens to this posterior mean? What role does theta have once you get a big sample size? As n gets bigger, right, the 1 over n goes to 0. And as n gets big, that goes to 0. Because as you get big sample sizes, the influence of theta basically kind of goes away. So the expectation of this, given a sample, really is starting to look like y bar. And this is not exactly perfect, math in terms of writing limits and stuff like that. But an interpretation that's given that is as you get bigger and bigger data, that prior choice, what was theta? What was your initial exponential? Was it really steep? Was it really flat? Whatever you chose. To get enough data, the posterior distribution is dominated by what the data are. So your inference about where's lambda where's that average rate, is going to be like the average across the different areas of the data that you have. Right? So the data end up being more important in bigger samples than whatever your initial guess was. In smaller samples, there's more of a trade-off between them. Right? So anyway, in a class like mathematical statistics, you know, we think, like which is 252 in the fall, we think about some of these things. Right? If you want to do inference and state things, you know, how do you take these probability distributions and then make conclusions about what the parameters are? Bayesian inference is one style, and we get things like what's the trade-off, you know, what influence does the prior choice have versus the amount of data you have, and how does that work? Right? But anyway, this would be the generalization of that case. You know, thinking about an application where we don't just have, you know, one area of this, but this is measurements of something like the number of measles cases around London, using this exponential, you know, Poisson, exponential prior, and then figuring out that you get a certain posterior distribution. So anyway, to me, that's where these things would be useful, and knowing this kind of hierarchical modeling and other work with probability distributions enters into statistics and figuring out and trying to discover things in the world. So. But you know, on the exam, you know, it'll be pieces of this. Right? Some of the chapter 5 material, but I'll try to, you know, write it, of course, so that it's doable in the time that you have. You need some time to think about the problems and write. But if you make a good study sheet, are familiar with some of the distribution methods, and can go quickly through, you know, parts of it, then that will give you more time to do the other parts. Any other? Well, why don't we stop there, and you can go study over the weekend. I'll post a little bit of information like that discrete problem from the other class. And don't forget to submit your homeworks. Great.
Projects, or is it online?
It is online. I have a.
Jesus.
There you go.
Unfortunately, forgot to print F, G, and H for that time. Two kind of copies out here always.
Sure. Yeah. So it has to deal with the binomial.
Okay. Yeah.
So if it's in trial, that would be a kind of piece.
Okay. Yeah.
And then the expectation of in time. It is. In time.
Okay.
So you have to have the binomial.
Okay, awesome. Thank you.
I was blown away.
That's awesome. I'm so glad for you.
I'm so happy. All in one night.
Do you know if, like, the last exam, these homeworks will be available before?
Yes.
Okay.
I mean, so I'll try to grade them.
All right.
Completely now, make them done by.
No,
I know
yeah, no
sometimes,
rush, but I
yeah,
just want to know if,
so-
like, I'd be able to see it again. before
And,
the exam.
I'll put the solutions on. So you know,
Oh, okay.
see how many I have.
All right, great. Thank you.
I have a question about B and C. There was a line in the assignment that said something like, for these values of alpha and beta.
Oh, yeah.
Did you want us to plug in?
Doing it in general is fine. It's, you know, really that line should have been kind of, at the point of evaluating numerically, the variance and comparing that to the mean and comparing it to the simulation. So, yeah, this is fine.
Yeah, I got a little lost because I said I did B with like alpha and beta plugged in, and then when it came to trying to do C, it was like it didn't make a whole lot of sense without. Anyway, right. Did I print out our stuff, or is like writing down?
Writing down the summaries from that is fine.
Yeah, for, like for H, I think I just wrote down what the simulated expectation.
That's fine.
Okay.
But, you know, and it didn't specifically ask for that, but, you know, in looking at the commands and the output, you get a little sense of what it's.
Yeah, it was like, it was almost, the first one had like sort of went up and then down again, and the second one peaked to start and then consistently. Are you like going to like a conference or something next Thursday?
No, no, it's more of a family thing. The spring break for the middle school starts that week. So mostly we were here, but it's one of my daughter's birthdays and a cousin's birthday, and then she has twin friends in DC who are having a bat mitzvahs together, and so just like everything kind of came together, and so we just kind of planned to do this and take the one day, and you know it takes a while to look at the projects and stuff, so that's what it is.
Have a good rest of your day.
Yep.